Hello everyone. I'd like to take a look at another example where we will be finding the resultant speed and direction of a vector. However, in this case, we do have some new tools available to us, some more ways that we can work with vectors. So I want to use those things in this example. All right, so the example says, the soccer player running forward at 7 meters per second kicks the ball with a velocity of 30 meters per second at an angle of 10 degrees with the horizontal. What is the resultant speed and direction of the kick? So we have two vectors going on here. We have one vector that represents the soccer player, and then a second vector that represents their kick. The speed of each of these, 7 meters per second, 30 meters per second, that is the length of the vectors, that's the magnitude. And then we do have one direction here, so an angle of 10 degrees for the kick. The soccer player running forward, that's just moving, for example, due east. It's just a one-dimensional measurement there. But let's start with just sketching out each of the two vectors. So we have one that represents the player, and then we have a second vector that represents the kick. So nothing too fancy here. I'm just a little sketch so we can think about the situation. So the player is running forward, so something like this, straight along that x-axis maybe, and the magnitude of that vector, 7 meters per second. So that's how long it is. And the kick, so an angle of 10 degrees with the horizontal, so it's just a little angle, and then this has a magnitude of 30 meters per second. Okay. Now, what we could do is we could take these two vectors, we could combine them together. Where this one ends, we could start the kick vector, and then we can draw in our triangle. We can use things like the law of cosines to help us find the speed and the direction of the resultant vector. However, we do have some new ways that we can work with these. So instead, what I want to do is I want to find the component form of each of these vectors. And once I get the component form, it becomes much easier to combine these together. Okay. The component form for this one's really easy. It has no vertical movement, so our component form is simply 7 in the x direction, 0 in the y direction. All right. Now for the kick vector, we are going to have to do a little bit of work to find the component form, but we do have a way to do that now. In previous lessons we talked about, so the component form for this vector is the magnitude times the cosine of theta, and then the magnitude times the sine of theta. All right, so if I draw in the little right triangle here, so if I drop that down, this is our change in x, and this is our change in y. So using trig, we can find those two pieces, and that's our component form. So let's see what we end up with here. So we have 30 times the cosine of 10, and then 30 times the sine of 10. And I'm just going to get an approximate for each of these. So we have 29.5 in the x direction, and then 30 times the sine of 10. We end up with about 5.2 in the y direction. All right, so now that we have the component form for each of these, to find the resultant vector, we can simply add these two together. So the resultant vector, we'll add our two together. So we end up with in the x direction 36.5, and the y direction about 5.2. Now if I sketch that out, just to relate it back to our original two vectors, so 36 in the x and 5.2 in the y, again, what it looks like doesn't necessarily matter. So this is 36.5, and then the y is 5.2, and where we could get that from is if we think about our other two vectors, we go 7 here, and then 30 at an angle of 10. So here's an angle of 10, this is 7, and those are our two original vectors, right? But what we need to find out is we need to find the length of this vector. Okay, so that's the resultant speed, and we need to find the angle. So we need to find the angle with the horizontal here, which we'll call theta. As you can see, I have a little triangle here, so we have lots of tools we can use. We can use the Pythagorean theorem to find the length. We also defined the magnitude, so I'm going to call this vector r. So the magnitude of vector r, okay, this is basically the Pythagorean theorem, but it's the square root of a squared plus b squared, which those are our horizontal and vertical components. So 36.5 squared plus 5.2 squared, square root of all that. Okay, and 27.04, and then we'll add those together and take the square root. So I end up with a magnitude of about 36.9. And in this case, just looking at what we started with, this is going to be meters per second. So the result of running forward at the 7 meters per second and kicking it at 30 meters per second, we end up with about 36.9. All right, then the other thing was we need the direction. So to do that, we can take a look at the tangent, because we know the opposite side and the adjacent side. So this is b over a. So the tangent of theta is equal to 5.2 over 36.5. And then the inverse tangent of both sides will give us our resultant direction. So let's see what we end up with. So 5.2 divided by 36.5, inverse tangent of that, we end up with a direction of about 8.1 degrees. So there we go. So the resultant vector here, not quite, it's a little bit smaller of a direction. And that's because we have this forward momentum pushing it along, so that kind of minimizes that angle a little bit. And then it does end up being faster because we need to combine that forward force with the force of the kick, so that vector does end up being a little bit longer.